Hi, good afternoon, everyone. I hope everyone can hear me clearly. Welcome to our webinar session today. We have two of our in-house geospatial specialists presenting today with two different topics. Now, first up will be Vincent, who will be presenting on 3D geodata, making sense of the world, followed by Stephanie. She will be presenting on GeoAI, computer vision and image recognition of geospatial data collection of doorway points of interest. So I will now hand over to Vincent, and Vincent can start presentation.
Hi everyone. Let me just share my presentation. Okay. So I'll present about this 3D geodata and how we are looking at it from what we call as a digital twins perspective. So with 3D geodata, which is a very rich information for geospatial systems, it contains a lot of information and is able to connect to other types of data because of its location properties. And this gives us unlimited potential to explore various ways of working in this virtual world. So maybe I'll just give a very quick introduction to, say, the digital twins that we are looking at. How do you build your own, say, your 3D twin with your 3D geodata and defining what's next in your use cases right from what you are looking at. So just a very quick introduction to this. So for digital twins, I think this is a very common term like for the past few years that all the companies have been defining in their own domains, in their own context, say from your GE looking at digital twin that drives their businesses to Microsoft looking at digital twins that looks at the different assets in your processors and to their IT systems. I think that's a lot of things that is ongoing in the different domains. And digital twin, I mean, in general, when we summarize and look across all the different definitions, everyone is trying to bring across a realistic digital model for the physical asset, and that you must connect to the real world and how you can use such information to better optimize this asset, either through its use, through its process, or anything that you can actually think of. And what connects all these is really the 3D geodata that we'll be looking at. So if we look at the different technology enablers across this ecosystem, things like geoinformation systems is very important to bring everything into the context of where you are and how do you travel to one place to another to bring about all these other innovations, say be it your 5G, putting in your greater bandwidth for such data transfers, to even your say your BIM models, your built environment to better understand your own environment itself, and down even to your all your other sensors data to provide you with even more granular information. So when we look at the different initiatives across, say like in Singapore's context, you can see some of these examples, be it from like NUS, looking at the digital urban climate twin to understand our coolings, to like say Surbana Jurong looking at a VR city. I think there's a lot of different initiatives and trying to bring forth their expertise in each of their domains. So when here's some more examples. So like the recent like topics on climate change, I think that's a very interesting area that where digital twins and the 3D geodata could actually play a role in defining the path forward in the climate change strategies. And when we look at, say, our own infrastructure itself, there's a lot of potential for that to improve the efficiencies in that area. So not only when we bring in the simulations that we are familiar with, say your traditional hydraulics, your traditional electrical network simulations, but when you put onto a 3D information platform, that really makes sense to a lot of people, especially those in operations on the ground, because they are able to relate to in terms of the physical space, they are able to relate to in terms of the physical assets on the ground. So it's more stuck to them if they notice any things that could change or even improve in the systems. So when we look at the digital twin itself and the 3D geodata, maybe we can do a start on looking at what are the different data that is out there and what we could actually play with it. So the hurdle is not high, I would say. So nowadays there are a lot of data that is made available on the internet. It's a very wide repository out there. So like for Singapore itself, there is an open data that was created for HDB using the OpenStreetMap data, as well as data sets like from the data.gov to create these 3D building extrusion models. And when we look across in Asia itself, we have Japan, where they develop all these models, the 3D data for over 56 cities. And it's a very rich data set that you can see over there. And even in Netherlands, they have this 3D back viewer who will be able to let you download their data by selecting like certain areas. So there's a lot of data sets out there you could explore, play around with, trying to make sense of your built environment. So there are also a lot of tools that is out there that people are using to explore. So right from your own desktop, you'll be able to use some open source tools and even trial tools to help you perform some of these 3D visualizations and try to link with your own data sets in the traditional 2D geospatial sense, for example, your shape files, etc. So this would provide you with more information and making a better sense of what you can actually explore in the future. And down to say when you use ArcGIS, which is very which has provided a very interesting tool to even do some procedural modeling and building your textures. So you could have data that actually looks good, right, with your open data. So when you have your 3D geodata, your models, and put it in together with the other information out there, what could you do? For example, when we look at like topics like climate change, I think the first thing that comes to mind to a lot of people is talking about like solar potential. So like in a built environment, solar potential is when people explore solar potential, they always talk about the rooftops. So you could actually calculate some of these using like brief estimations and visualize them by embedding, by combining the two data sets together. You could also try to bring both what you have explored into your other platforms. For example, your dashboards, be it you are using Tableau or using ClickSense, you can put some of these together so that you could convey the story about, say, your solar potential, or convey your story about your data that you could visualize both in terms of the traditional methods as well as in the 3D geospatial sense. And with all these possibilities of data, I think it comes to mind to everyone to really define what's the next that we could explore. I think that really boils down to all your very specific domains. I see a lot of experts today in their specific domains. So maybe I'll just share the team, what we are working on, and the references that we always look towards to. So for example, like when we look towards the industry, we are also quite impressed with what GE has done over the years in their digital wind farm projects, and where they put their platforms together and put their systems in place together. They could actually boost their bottom line. They are boosting their production, improving their profits. I think that's a very good way for the industries to embark on, and also trying to bring more value to the market itself. And when we look at the wider context, for example, like city planning, that's I think is close to like SLA's heart and our planning agency's heart, is to how we better make decisions for each and every topic. So when we look at like Helsinki's efforts in these areas, there's a lot of information that they have put online and helping their industry over there for their say the geothermal energy and their electric solar energy providers to better plan their infrastructure. I think there's a win-win situation over there where the planners benefit from better planning and the industry benefits from more opportunities that are made visible in this type of information sharing. And when we look at, say, in Italy itself, where they combine data sets from all the other sensors, and they try to integrate into their operations, I think it provides that additional value add and efficiency to the whole network systems that they have for their road networks to their other networks also. And when we look to the high-speed 2 project in UK, then when we know there's a lot of work that is being done to bring forth all this information together for better construction as well as planning. And in Singapore's context, we have the Singapore Authority looking at the Tuas terminal, where like Singapore's terminus is one of the most efficient, and they are pushing the envelope further, looking at all these optimizations. So when we look at the different initiatives out there, we also want to learn, say, from the various government agencies, looking at how they define the path forward. So I think that's a very important part when we want to define that twin and the type of data that we want to bring onto the platforms and any other solutions that we want to look at. So when we look towards, say, for UK itself in terms of their works, I think there are very interesting principles that they have put forward. For example, like public good to the evolution of the systems itself. I think it helps to keep the systems always up to date with the different technologies, as well as always up to date with the needs on the ground. I think that's a very important way for systems moving forward, because technologies are always evolving, but we also need to keep evolving our systems to keep pace with the demand from the citizens. And when we look at digital twins in the initial steps, we also try to understand if there's any framework that could help us better prioritize certain efforts. So from the UK Connected Places Protocol, I think there are some criteria that they have put up and aligning with, say, your key priorities in the near term to the longer term. I think this is one that helps us both as planners as well as how do we encourage the industry to move forward with us. And when we look at the different objectives of all these different digital twins, we can see there's a wide range of topics that people are looking at nowadays. So like the top one, I think nowadays that is on everyone's mind, at least in Singapore's context, is the climate change part, where we look at things from, say, your EV deployment to improving or increasing your solar deployment. And when we look at our communities here in Singapore, how do we bring the communities together? So there is talk about, say, your kampong spirit, etc. But how do you like rejuvenate like certain places, especially after this COVID itself? And for infrastructure, there is always a long-term planning that is required. So to keep the city updated and moving fast forward. So when we look at the different stages of technology, we came across also Australia's digital twin maturity model, which is very interesting, where we look at the different levels of skills expertise that is required in each of these different technology stages. So this is very important in all these different initiatives, because you may not need all of them to be in place before you embark on some of these initiatives. So for example, like if you have data today that is related to sensors, and you have open data that is related to, say, the 3D models itself, there is already that availability to integrate over there and to analyze what is in there and the value add forward, even though that you are not embarking on some of these intelligence at this point in time. So I think that's a very staged approach, and for different companies out there, I think that it is good to help them also plan this in terms of their expertise and how are they moving towards in terms of their technology. And when we look across all these different digital twins in the different countries, we also come across all these different ecosystems that everyone is trying to build in terms of the digital side of things. So because of its different needs across different domains, the federated ecosystem is a key or the main mode approach to all these digital twins. But the data side of things is where there is to be clarity in terms of the governance, for example, like custodianship and authority, and down to the technical details like interoperability. So this will help drive some of these digital twins initiatives and help to deliver or even develop new products and better services for the industry. So now I've come to the end of the presentation, and I think for the previous, we have just launched the OneMap 3D. So do go ahead and see what you can visit and also make sense of in Singapore's new 3D. So thank you very much.
Thank you, Vincent. So next up, we have Stephanie with her presentation.
Hello. Can you all see my slides? Okay, great. So today I would like to share a bit more about AI and its applications in GIS. A quick overview of my presentation. First, I'll give a very quick introduction to AI, and then I will show you an example of how we are using computer vision to help us in geospatial data collection. And finally, I will share some other examples of how AI can be potentially used in geospatial. So first, a very quick introduction to AI. So the term AI, I'm sure everyone has heard of it. And basically what it means is that um, it refers to any technique that kind of allows computers to kind of mimic human intelligence. So AI is actually quite a broad term and can cover anything from like using logic-based rules to maybe machine learning. So machine learning itself is a subset of AI. And so what exactly is machine learning? It can be defined as the field of study that gives computers the ability to learn without being explicitly programmed. And this is typically done using statistical techniques that enables machines to improve at tasks with experience. So one way that this can either be done through supervised learning or unsupervised learning. So for supervised learning, what this means is that typically you would give the computer the desired solutions or labels, and for unsupervised learning, the training data is unlabeled. Some examples of machine learning could include like classification or categorization, regression, as well as clustering. Normally, like classification and categorization and regression are forms of supervised learning, while clustering is a form of unsupervised learning. So on top of this, another term that we commonly hear is deep learning. And what deep learning really is a subset of machine learning that's typically used for image and speech recognition. So how this is done is that it allows the computer to learn by passing very, very large amounts of data through neural networks. Because there's not much time today, I won't go too deep into what neural networks are, but I'll try to give a very, very quick explanation. So neural networks typically try to mimic the operations of the human brain, and they consist of a collection of connected nodes, as you can see in the picture in the slides. So typically at the start, you will have like an input layer. So this layer, in terms of like if you want to use image data, it will be the pixels that actually make up the data, or maybe an aggregated value of these pixels. And then we also have the output layer, which is actually the final categorization or classification of the image, which is also given to the computer. So when we train the neural network, the middle portion, which consists of layers and is typically known as the hidden layers, these layers are like connected by edges, and what the computer will try to do is assign a weightage to each of these edges, which will then compute to an output value at each node. And after many, many of these computations, a value is assigned to the output layer. And the output node with the highest value is typically considered like the correct output. So today, actually what I would like to share about is the application of such computer vision techniques in the collection of geospatial data. So one of the most common computer vision tasks is the image classification task. So basically, image classification, it will look at an image as a whole, and it will try to understand what the image itself contains and assign it to a specific label. And one of the most popular examples of this is the classification of the MNIST dataset. So this dataset actually consists of a database of handwritten digits, as you can see here. And there are about 60,000 training set images and 10,000 test set images. So it's really a lot of images. So in this example, basically the model will have 10 categories to choose from. So it can choose from the values 0 to 9. And basically what the image classification does is the labeled data is fed into the neural network, the model is trained, and then the weights are iteratively assigned to each edge until an optimum point is reached. And then the model will be considered to be trained. And then what we can do is we can use this model to try to classify an image that it has never seen before. So for example, like in the example here, we can put in this handwritten 5, and then the model might hopefully correctly outputs 5 as an answer. So image classification is a very common task. So besides being able to identify handwritten image, what we were thinking of is how can we actually use image classification to help with the collection of geospatial data. And so what we came up with is that we are actually trying to use this technique to help us in the collection of what we term as doorway points of interest. So actually how we define doorway points of interest is the connection points between different spaces. And the examples of this would be like entrances, lifts, stairs, and escalators. So we are looking to collect these doorway points actually because we believe that such data provides multiple benefits, including like providing last mile details that can help pedestrians navigate more easily and can also potentially enhance the business update and map creation process amongst many other applications. So how have we gone about this? The very first step would be to collect and label the data. And for us, because we want to train our model to be specific to the Singapore context, we have typically done this through manual site survey. So actually we did try to look online to see if there were any image sets available, like maybe through Flickr or all those different image collection sites, but we couldn't really find a suitable fit. So what we actually have to do is to go down and manually survey on site ourselves. And then, so as mentioned before, we then labeled the images into 4 categories that we are classifying. So what we are actually interested in would be the entrances, the lifts, escalators, and stairs. Then we will use this data to train our classification model. So actually, these are just some examples of the outputs of our training. And so on the left, you can see that this was our first pass when we tried to collect about about like 680 images in total to train and test our model. And so for the outcomes of this, we can actually see that we get accuracy of 82% on the training data and 72% on the test data. So one way that we try to improve the model further is to collect even more data. So for the second time we tried, it was about 1,000 plus images to try to train and test. And training and test accuracy actually did improve. So the training accuracy improved to 83% and the test accuracy improved to about 77%. But as you can see from the graphs here, right, actually it's not very smooth. And then so we try to evaluate why this may be. And especially for the loss graph, you can see that while it does show improvement, so there's like a downward slope, but there's a quite large gap between both curves and it's quite noisy and there's quite a lot of movements. So I think one explanation for this is that our data set is still quite unrepresentative because currently we are training and testing on about 1,000 over images, but when you compare this to like data sets like MNIST where it's just for handwritten images and there are already a total of about like 70,000 images. So really 1,000 plus images is really not a lot. So this is one key limitation to our model. But we do still believe that the model could be of use. And that is why we are now deploying it on our POC app called Pin2, where we will be trying to collect more of this doorway POI data. So what the Pin2 app actually does is that it allows the users to take a picture using the app, and then at the back end that we will run the image through our classification model, and we have also tried to employ this syntax recognition model, and then the algorithms will automatically classify into what category it is. And for the syntax part, it will also try to extract like the maybe the name of the shop or whatever text you can see in the images. So just a quick aside for the syntax part, we actually are also trying to evaluate what models are possible to use for syntax detection. So this is just a very quick overview. And this is actually what the actual app looks like. So it's very simple to use. The user will just take a photo of the doorway POI in question. And so in this case, it's actually an entrance to a restaurant. Then the app will extract the location information and place the point of interest on the map. And the user can actually manually correct this location if it's needed to be corrected, because usually in like urban environments, the GPS signal may not be too good. And then after that, we will have a simple form. And the classification model will actually auto-categorize the image and fill in the category over here. But if the category is wrong, the user can always change it. And so for the syntax recognition part, we also use it to actually help to autofill the name. So once the user clicks submit, the point is saved. The point as well as the image is saved into our database. Yeah, so besides collecting doorway POIs itself, a key benefit of this app is also that it will help us collect more data that in the future we can use to train our model with again. So it does add to the training data that we have. And we hope that through the collection of more data, our model can continue to improve. However, another key limitation that we have actually noticed in the model is that so actually to illustrate this, I'll just show you 3 images on the slide here you can see. So for each image, you can actually see that there can be more than one classification. So like in the first one, we can see both stairs and an entrance, which is like the door. And for the second one, we actually can see both escalators and stairs. And for the third one, we see both a lift and stairs. So these images are very typical of our everyday life. And while we as humans can like easily recognize the images shown, the objects shown here, like a simple classification model will not be able to do so, and it will only assign to one specific category. So actually, one way that we have thought to improve this is through the use of instance segmentation modeling, which is another form of computer vision task. So actually what instance segmentation does is that it will delineate each distinct object that appears in the image, and the algorithm actually will classify the image pixel by pixel to actually show what each pixel represents. So we've actually done some evaluation on what models that we could use, and so far we have tried to evaluate Mask, RCNN, and Detectron 2. And actually for Detectron 2, we did try to train a model with some of the data that we have, and the results do appear quite promising. So as you can see in the images here, right, the model can actually detect like objects within the image that maybe even humans may not be able to detect. So let's just take the first image on the top left, where it's a photo of a stairs. Like for me, I think I would only have noticed the stairs, but the model is actually able to recognize the shop fronts behind it as well. So this is actually the same for the rest of the images shown here. And if you see on the bottom right, the middle picture, it can even detect like really small things, like maybe just a step up to the door, which can also be very useful information for us. So actually, this model, one downside of it is that to actually train the model, we will need to annotate quite a lot of data, and it can be quite time consuming, because for each image, somebody will have to draw out each object, and we do need to quite a large data set to be able to train a good model. But so far, the results do seem quite promising. So this is something that we are very keen to explore further. So besides this project, actually, I would also just like to take some time to share a bit more about the other applications of AI and geospatial. So to give some examples, right? So another way that we can use computer vision in geospatial is maybe through like to process satellite imagery. So one example would be like maybe we can use satellite imagery to identify cars. So by using this AI, we are actually able to count the number of cars currently in the image, and then so this data can then be used to help us improve our understanding of the traffic conditions in a particular area. And other than this, we can also use the computer vision techniques to kind of like remove the cars and clean out our satellite imagery before we publish it. Another example of AI being used is that it can even be used in like predictions. So we can actually use it to train a regression model. For example, over here, I'm showing an example of how the AI can be used to train a model that can help to predict HDB prices. So we can take different attributes. So when we think about like the pricing of HDB, we'll probably think about like what's the floor area, what flat type it is, and what year it's built. But actually, we can also combine it with geospatial attributes like the let and long, or maybe we can calculate something like the proximity to the city, or maybe the proximity to the nearest MRT. And using this data, we can actually train a regression model that can potentially be used to estimate the price of a HDB, sorry. And so actually we actually did map this out on the map plot, and we can see that actually what the estimates are for the cheaper flats to the more expensive flats. So typically we see like the more expensive flats are located towards the city center, and the less expensive flats probably further away from that. So finally, one last way that AI is quite commonly used in geospatial analysis is through the cluster analysis. So I'm just going to give two quick examples. The K-means clustering and the dbScan are two clustering algorithms that are very, very commonly seen in geospatial analysis. So these two algorithms actually serve to cluster groups of spatial objects. So they are slightly different, and depending on like what your use case is, you can see how you would like to use them. So for K-means clustering, actually it will be like more of a partition-based clustering. And so basically what it does is that it will partition all the points into a sample space into a set number of groups of similarity. And so for this, the user will actually need to input the number of classes that you would expect to see. And for dbScan, on the other hand, it will be more of a density-based clustering algorithm. And the algorithm, basically, the user itself would not need to input the number of classes they would expect to see. So actually, through using such algorithms, we can help users better understand some of their problems. So for example, it can actually help retailers understand like where their customers are clustered and how they can like target their marketing towards these groups. And then besides this, we can also see that maybe it could help in the understanding where certain groups of residents are clustered to maybe determine where's the best location for like specific infrastructure. So for example, like maybe where are young families more clustered so that it can help determine like where's the best location to build more playgrounds. And then finally, we can also use it maybe for health risk analysis, where we can potentially find where the clusters of a certain incidence of illness are, and then study the surrounding environment to maybe determine any possible risk factors or how we can also mitigate them. So these are just some very quick examples. So these are just a few of the many applications for of AI for geospatial, and I think it'll be very interesting to see how this field continues to develop. And yeah, I have come to the end of my presentation. Thank you.
Thank you, Stephanie. So I think what we need to do now is to see if there's any question from the audience that they would like to pose to Vincent and Stephanie. You can type in the Q&A tab that's on your right, on the right panel. Well, I guess if we have no questions from the audience, then we can close the session. Thank you, Vincent. Thank you, Stephanie, for your presentation today.
Thank
And I hope
you.
all of you enjoy the webinar session today. Thank you.
Thank you.